Users saw inconsistent cart contents, items added on one device disappeared on another. The root cause, a network partition between two data centers where both sides accepted writes independently because we used eventual consistency with no quorum enforcement. Here's exactly why. But first, let's cover the basics of designing a distributed key-value store. Welcome to TheCodeForge. Before we dig into that production issue, let's cover design a distributed key-value store. A distributed key-value store is a system that stores data as key-value pairs across multiple nodes. It uses techniques like consistent hashing for partitioning, replication for durability, and consensus algorithms for consistency. Think of a giant library where books are stored across many shelves. Range partitioning sounds simple, but causes hours-long rebalances when nodes are added or removed. Consistent hashing solves this by mapping keys to a ring of hash values. Each node owns a set of hash ranges. When a node fails, only its immediate neighbor takes over its keys. Here's a Java implementation of a consistent hash ring with virtual nodes. The ring is a tree map of hash values to node IDs. When adding a node, we add multiple virtual nodes to spread load. The getNode method finds the nearest node clockwise on the ring. Replication is your safety net against node failures. Choose a replication factor n, typically 3. For each write, you need W acknowledgements. For reads, you need R acknowledgements. The formula for strong consistency is W plus R n in production. I default to n equals 3, W equals 2, R equals 2. Here's a configuration class for replication. The assertion ensures strong consistency. Never set W equals 1 in production. A single node failure causes data loss. I've seen a startup lose all user sessions because they used W equals 1 and the only replica died. When you need strong consistency across replicas, you need a consensus algorithm. Raft is designed for understandability and has become the de facto standard. It elects a leader that handles all writes. Followers replicate the log. If the leader fails, a new election happens. Here's a simplified Raft node state machine. The node starts as a follower. If it doesn't receive a heartbeat within the election timeout, it becomes a candidate and starts an election. Set election timeouts to at least 10x the expected round-trip time to avoid thrashing. When a node is unreachable, the coordinator temporarily stores the write as a hint. When the node comes back, the hint is replayed. This prevents data loss during transient failures, but if the coordinator fails before replaying, the hint is lost. That's where red repair comes in. Here's a Java implementation of hinted handoff. The storeHint method saves a hint for a target node. The replayHints method sends all hints for a recovered node. I've seen a production cluster where hinted handoff was disabled. When a node went down for 10 minutes, all writes were lost permanently. When concurrent writes happen to the same key, you need a conflict resolution strategy. Last write wins uses a timestamp. The write with the latest timestamp wins. But clocks aren't reliable, so use hybrid logical clocks instead. CRDTs guarantee convergence without consensus. Here's a versioned value class for last write wins. The isNewerThan method compares timestamps with noDid as tiebreaker. Don't rely on wall clocks, use hybrid logical clocks that combine physical time with a logical counter. You need to detect node failures quickly, but avoid false positives. Gossip protocols spread membership information across the cluster. Phi accrual failure detector tracks heartbeat interarrival times and computes a suspicion level. If Phi exceeds a threshold, the node is considered down. Here's a Java implementation of Phi accrual failure detector. It maintains a window of heartbeat intervals and computes the probability that the current elapsed time exceeds the expected interval. If Phi exceeds a threshold, the node is suspected down. This is the same issue we highlighted at the start. Here's exactly why that happened. A network partition between two data centers caused both sides to accept writes independently because we used eventual consistency with no quorum enforcement. Each side had a different version of the cart for the same user key, leading to inconsistent cart contents. The fix was to switch to Raft consensus with a 3-node cluster per partition. We set write consistency to quorum with W equals 2, R equals 2, N equals 3. We added a proxy layer that routes all writes for a key to the leader. This ensures that writes are acknowledged by a majority before returning success. Eventual consistency without conflict resolution is a ticking time bomb under network partitions. Always enforce quorum for critical data. Set write consistency to quorum W equals 2, R equals 2, N equals 3 to ensure strong consistency. If you use MD5 for hashing, you'll get decent distribution, but Murmur hash 3 is faster and more uniform. I've seen a production cluster where 30% of requests hit one node because the hash function was biased. Switch to Murmur hash 3 or City hash. I've seen a production cluster where hinted handoff was disabled to reduce write latency. When a node went down for 10 minutes, all writes to that node were lost permanently. The fix: enable hinted handoff with a reasonable timeout of 3 hours. Don't rely on wall clocks for LWW. Clock skew between nodes can cause newer writes to be overwritten by older ones. Use hybrid logical clocks that are monotonic and work without NTP synchronization. If your gossip protocol uses a fixed heartbeat interval, a network hiccup can cause false failures. Use phi accrual with a window of at least 1,000 intervals. Set phi threshold to 8 for aggressive detection, 12 for conservative. The article uses Java Security, Message Digest with MD5 for consistent hashing. In Java 9+, MD5 is still available but considered weak. For production, use Java Security Message Digest. Get instance, SHA-256, or switch to Murmur hash 3 via library like Guava's, hashing Murmur 332. Also, the tree map sealing method works correctly, but ensure the hash function produces non-negative integers to avoid issues with negative keys. The article mentions gossip protocols, but doesn't show code. Here's a simple gossip membership protocol that periodically exchanges node lists with a random peer, using a failure detector to remove dead nodes. The article sets hinted handoff timeout to 3 hours, but in practice, if a node is down longer than that, hints may accumulate and cause memory pressure. Monitor the hint queue size and consider using a persistent store for hints, e.g. local disk, to avoid losing them on coordinator restart. Also, ensure the timeout is configurable per deployment. Here's how to diagnose and fix common issues. For stale reads, check consistency levels and run red repair. For write latency spikes, check hinted handoff queue size and monitor disk I/O for split brain, check network connectivity, and ensure quorum size N2. Let's run through some common interview questions. How does consistent hashing handle node additions? Only keys in the new node's hash range are reassigned, minimizing data movement. When would you choose Raft over Paxos? Raft is simpler with a strong leader. Paxos is more complex. Use Raft unless Byzantine fault tolerance is needed. What happens when a Raft leader fails during a write? The write is lost if not replicated to majority. A new leader is elected, and uncommitted entries are discarded. And a few frequently asked questions. What hash function is best for consistent hashing? Murmur hash 3 is fast and uniform. Avoid MD5. What's the difference between eventual and strong consistency? Eventual converges over time. Strong guarantees latest read. Use strong for critical data. How to handle node failures. Use hinted handoff for transient failures, red repair for permanent, and phi accrual for detection. To recap, use consistent hashing with virtual nodes for partitioning. Always enforce quorum for strong consistency. Use Raft for consensus. Enable hinted handoff to prevent data loss, and use phi accrual for adaptive failure detection. Ready to go deeper? Up next, design object storage, simple storage service, then design a proximity service, then design Ticketmaster. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.